to talk about AC impedance. So far, we've largely been talking about large changes in potential and measure current, right? Those are most of the experiments we've done. We've actually swept the potential over a volt range. We've changed the potential a large degree. And we measure current as a function of time. And what you do in AC impedance is now we perturb system. So the system is our electrode and our counter electrode and a reference electrode, the electrolyte, with small AC perturbation or signal and follow system at steady state. We'll see what I mean in a second. So basically, as this perturbation is getting applied, you see what happens to our system. And there's some advantages to this. We get higher precision in principle because we're going to make a steady state measurement. We can do averaging, etc., to get very high precision, and we can affect the sort of the time scale we're accessing by the frequency of our perturbation. Okay. And another thing we can do is we can treat the response of system as linear function of perturbation. We can do that because pretty much any function you look at, right, if you look at it on a small enough perturbation, it looks linear, right? So we can use a sort of if you want to think about it, it's a Taylor series expansion of the perturbation, of the response to the perturbation, and that Taylor series expansion is going to be dominated by the linear component if it's a sufficiently small perturbation. And we can go from 10 to the negative 4 to 10 to the 7 hertz and access a very wide range of frequencies and hence time scales that the system is responding to. Okay, so that's why we do AC impedance. Are there any questions there? A hertz is just defined as one per second. So 1 hertz would be 1 oscillation per second. So we're going to see that we're going to apply an oscillatory perturbation, for example, an oscillatory voltage input, and we can characterize that oscillatory input based on its frequency is related to the inverse time of a period. So before we do this, though, we need to understand a little bit about AC circuits and how we characterize them. So we'll do a very simple but effective treatment of AC circuits here so you can analyze or at least understand how all these electrochemical circuits are analyzed, right? And the idea here is we want to build, for example, an equivalent circuit that represents our electrochemical cell, where we might have some capacitances and some resistances that represent different processes in our cell, and we want to use impedance to deconvolute the actual capacitances, for example, of the electrode, charge transfer resistances due to Faraday processes, series resistances, and the cells can get much more complicated than this. We can have 10 or more circuit elements in there, and we want a way to use all this frequency data to understand what the fundamental processes going on in our cell are. In general, impedance measurements, and you guys have done these in the lab, right? You have applied a frequency sweep with a small AC bias to extract the series resistance of your electrodes, of your cells, right? The uncompensated series resistance. So we want to apply a small AC signal to the working electrode. And we're going to call that signal E. And it's going to have some maximum magnitude, big E. And it's going to modulate as a sine wave with an angular frequency, omega. So omega is the angular frequency, and omega is equal to 2 pi times the frequency. And you'll see why this is useful in a second. This is time. And this is the maximum max. So let's think about what that wave looks like. That's a waveform, right? It's a sine. So could everybody in your notes draw this function? Draw E as a function of t. Yes, sine waves start at 0, cosine waves start at 1. No, it's a sine wave. And now we need to think about where is it going to cross 0 again, right? Because there's going to be a positive and a negative lobe. Now, a sine wave, what's the maximum amplitude of just the sine part of this? Maximum value you can take is 1, right? So the maximum value of this function is what? E. The minimum value is what? Negative E. Sine wave is going to be 0 where? At t equals 0, right? Where's it going to be 0 again? Pi over omega. So why do you say that?
Because
so sine of pi. So pi is equivalent to 180 degrees, right? So 2 pi is equivalent to 360 degrees. Pi is equivalent to 180 degrees. Angular coordinates, right? So if I let t go to pi over omega, I should have another 0 point. Well, where's another 0 point on this wave? T equals what? 2 pi over omega, right? Because the sine wave repeats itself at 2 pi. Okay, so it's pretty easy to draw this wave now. Right? There it is. Okay? More or less. And this is pi over omega, and this is 2 pi over omega. Okay, does everybody see this?
are we talking about like are we still at like some DC offset and we're wiggling in? Okay.
You can do that. So typically what you do is you control the DC potential versus the reference electrode. This is a very good question. So you control the DC potential versus the reference electrode that's at some fixed potential. And then when you're at that DC potential, then you wiggle it back and forth.
Oh, okay.
Now your DC potential might be 0 versus your reference, but of course your reference potential is arbitrary. It's whatever you're choosing as your reference. So yes, you always have to control the DC offset, practically. And you do that in the experiment, right? You go and you set the DC offset, and then you wiggle the AC potential on top of that. So this is going to be basically E, right? Represent this in something called a phasor diagram. I can think about a vector E. We're going to call that E dot. The dot represents it's a vector. And that vector is rotating. It has length E, right? It has total length E. And it's rotating. Okay. And the rotation in time tells you where we are on this sine wave diagram, because we can take E to be the x component of that vector. Well, would this be a sine or a cosine wave? Why did you say cosine? 0, the magnitude is 1, right? So this would actually be a cosine wave. That's right. So sine wave starts at 0, right? So t equals 0, or the argument of the sign is 0, then I have no amplitude. Little e equals the length of E dot, large E dot, at time equals 0 here. So this is actually a cosine, right? This is often used as the excitation or the modulation signal. We're going to wiggle our system around. And what do we usually measure? We measure the current response, right? So we're going to do that still. Now, what do you expect the current response to do with time? Is it going to be linear with time? Invariant with time? What do you think? You think it would follow your voltage? It might, right? It could. It's probably, you think it's going to be oscillating? I'm going to draw the current response. And this is just kind of how we define things, but I'm going to draw the current response. Here's the current. And it might be offset from the voltage signal, right? Okay. So this is, if this is E, this might be I. Okay. This is the function of time. And this is omega 2 pi over omega. And if I, this wave out here, this would also, so at some point, go back to 0. And this will be 2 pi plus some offset over omega, right? Some phasing. So this curve is out of phase from this curve, in general. They could be in phase, but they don't have to be. Are the amplitudes? The amplitudes have to be the same? No, because they have different units. They're, obviously, there's no reason for the amplitude of the current and the amplitude of the voltage in whatever unit you happen to choose to be the same. So they can have different amplitudes. Are the frequencies going to be the same? Generally, yes, right? Because you have excitation source here. It turns out you get harmonics and things like that, which we won't talk about at all in this course. But in general, yes, this would be the first harmonic response of the curve. So we get a sinusoidal current response with some phase shift. And we can analyze this in this sort of projection, actually. I can think about this as a current response that is phase shifted from my voltage or potential excitation. And you can think about these all rotating together in space, right? And that would give you these overlapping sine waves with the same frequency, but different magnitudes, different units, and a different phase. Question. So let's think about what various circuit elements do in this situation. So we're going to excite them with some source, and we're going to measure the current response, and we're going to think about them in terms of the magnitude of the current response and its phase shift relative to the excitation potential source. Okay? So what about a resistor, R? This can be circuit elements. A resistor. So what law typically describes the current response of a resistor to applied voltage or potential? Ohm's law. What's Ohm's law? Okay, so I'm going to write it a little different. I dot equals E dot over R. Okay, it's the same thing. It's E equals IR, right? But now these are vectors. But because Ohm's law always holds here for an ideal resistor, independent of the frequency, independent of the voltage, if I have a voltage perturbation, right? At any given voltage, I will measure some current, and the current will always be linear with the voltage, right? There's no reason for it not to be. Just because you're changing the voltage, if Ohm's law is working, if it's an ideal resistor, the current should always be proportional to the voltage. So these are in phase, right? Right? Phi equals 0. R is a constant. Now, in an electrochemical cell, the value of R might actually depend on your applied DC potential and things like that. But in general, R is going to be a constant in this analysis. These are the vectors, the phasors, I guess, that are describing the signal modulation and the current response, the modulation of the current response. There might be some DC, by the way, there might be some DC current that's flowing too. In this analysis, we're just measuring the current that's modulated, the modulated current. And so we have electronics that can pick up the current response at a given frequency. By the way, that's why in your lab, what did you look in when you did a frequency sweep to get the series resistance? You looked for a region where the phase shift was close to what? 0. You looked for where the phase shift went to 0, which happens at high frequency. And you'll understand why that is today. Okay, so now let's go on and do a capacitor. A capacitor is a little more complicated. So Q, this is going to be the charge on the capacitor. Q is equal to the capacitance. This is a geometric quantity related to the electrode under study, right? Or, in general for electrochemistry, we're usually talking about the electrode capacitance, but more generally, it's related to the geometry of whatever circuit element it is describing. So it's a constant, usually. And E times E. This is time varying potential. Right? And so this is just the definition of capacitance. I mean, I could write 3 lines here. That's the definition of capacitance. Right? It's how much charge do you store for a given potential. And now we're just time varying the potential. So what's going to happen to Q? It's going to vary with time. So should the current vary with time if Q varies with time? What's the definition of current? I equals charge per second. Those are the units, I should say. But if I wanted to write it in terms of charge, what would it be? dq dt, right? So we'll use that here in a second. Okay, so that's a capacitor. So its charge is equal to the capacitance times the time varying potential. So let's go on here. So we can also write dq dt equals c de dt. If I differentiate both sides, right? And of course, this is the current is equal to dq dt. So I think about a circuit. This is literally a circuit with one capacitor in it. And I'm thinking about the current flowing through that circuit under an AC applied voltage, right? There's some potential E on that capacitor, across that capacitor. It's time varying. Okay, so what's that equal to? What's the derivative of the time varying voltage source? Equals E cosine omega t c omega e, right? Because I need to take the derivative of the inside function and multiply it. So take the derivative of omega t, we get omega. Omega goes out in front. C was there before. E was there before as well in this formula. And how do I write this in terms of a sine wave? Sine, what is it?
Yeah. Omega t.
Omega t plus pi over 2. So this is seen easily from the difference between a sine wave and a cosine wave. So a sine wave looks like that. Cosine wave peaks here, right? So this peaks at pi over 2. Cosine wave peaks at 0. And so the phase shift equals pi over 2, right? Between a cosine wave and a sine wave. And we can further define something called the reactive capacitance, and write this, I equals E over XC. You'll see why capacitive reactance, sine omega t plus pi over 2. Okay? Where pi C is the capacitive reactance. So this is kind of like a resistance for a capacitive AC circuit. Right? Because what does this term go to? Its maximum. The sine term. 1. So that looks a lot like Ohm's law, right? So it's kind of Ohm's law for a capacitor under an AC excitation. And XC here, capacitive reactance, is defined as 1 over omega C. So you might remember that the capacitive reactance from your freshman physics course, as the frequency goes to infinity, what happens to this term?
0.
Goes to 0. What happens to the current? Goes to infinity. So essentially current flows freely through a capacitor at high frequency. Right? And that's because you're shuttling charge on and off these plates, right? And if you do that fast enough, you don't even realize that the plates are there. Right? Because you never put enough charge on to change the potential of the capacitor. Because you're putting a little bit on, taking it up, little on, taking it up, little on, taking it. You never charge the capacitor. So you don't lose any potential across the capacitor. So it's basically a short circuit, okay, as you go to high frequency. And at low frequency, as omega goes to 0, what does it look like? Infinite. So what does the current go to? 0. Does that make sense? So what happens if I have a perfect capacitor and I apply 10 volts across it? How much current do I measure?
0.
You sure? You measure 0. Eventually, at steady state. This is the steady state solution, right? Of course it will charge, and we did this, right? We actually did it in lab, and we also derived it. You'll measure something that looks like that, right? An exponential decay. So eventually no current will pass, okay? So what is the phase angle for a capacitor? Pi over 2. And which one's ahead? Or which one's behind? Is the current ahead or behind the voltage? So it looks like the current is ahead by pi over 2. Leads it by 90 degrees. Okay. Or you could say the current is behind by 3 pi over 2. It's actually equivalent, right? But this is how we'll represent it here. Okay, so we note for a capacitor, I leads, probably a phasor here actually, I leads E by pi over 2 equals 90 degrees. So often in electrochemistry software, they'll actually give the phase angle in degrees. So we can think about our phasor diagram. If we imagine we have I dot, and we have E dot, this angle, phi, equals pi over 2. This is for a capacitor. And to represent this phase, we use the complex plane. So what is the complex plane? Do you guys remember?
Yeah.
Okay, so we're going to make a plane, right? And we're going to have the y-axis be imaginary and the x-axis be real. Okay? And what we can do is we can say that E equals negative J, which is going to be a complex number, chi C I for a capacitor. So if we think about I, if we set our reference frame, where I is sitting on the real, right? This is the real plane, real axis. And this is the imaginary axis. And we set I to be on the real axis. E is perfectly aligned with the imaginary axis, right? For a purely capacitive system. And if it was a purely resistive system, D and I would be both on the real axis. So we can kind of set our reference frame to be I, and we can look at where is E relative to that based on some phase shift. This complex plane stuff gets complex. But it's just a way to represent the phase shift. It's a compact mathematical notation to represent a phase shift, basically. And if it's purely on the complex plane, it's a phase shift of 90 degrees.
Oh, quick question.
Yeah, imaginary, yes.
Okay.
Square root of -1. But this is nice, right? It's a very compact way of writing the relationship between the voltage perturbation and the current response in terms of something that looks kind of like a resistance. So not only is a capacitive response, you have to make your resistance essentially frequency dependent, right? That's what it's saying. So this is like Ohm's law. This is Ohm's law for a capacitor. Your response is frequent. Your effective resistance, impedance actually, it's actually the impedance of a capacitor. Impedance is the AC equivalent of resistance. Is frequency dependent. You also have to represent that the current and the voltage are not in phase. And the way we do that is current is imaginary, and on the complex plane, that means that's a phase shift of 90 degrees, and we're all done. It's all taken care of. Right? But more generally, I might have any phase shift. Okay? And more generally, we're going to write this, it's going to have both a real and an imaginary component to that response. So if phi is not 90, right, then you're going to have a real and an imaginary component to your, let's consider a series RC circuit. So everybody draw a series RC circuit in your notes, please. So we have a resistor, right? And I need to add a capacitor, and where should I put the capacitor? In series with the resistor. Okay, the alternative would be to write a parallel circuit, right? This is a parallel RC circuit. We're going to focus on the series RC circuit. So E, imagine I have some total time-varying potential modulation that's acting on this circuit, okay? I'm going to have some potential that's going to drop over the resistor and some that's going to drop over the capacitor, right? Because they each have an impedance or a reactance, so an AC equivalent of a resistance, right? And the capacitor, we derived it. It's this. So we could calculate how much, for a given current, how much is dropping across the capacitor, and we could calculate how much drops across the resistor. And we can write that as E R dot plus EC dot equals I dot R minus J XC. So this I've just combined. These are just Ohm's law again. Kind of. Well, this part is Ohm's law. And this part is sort of the AC ohms, in parentheses, law for a capacitor. In other words, it's just telling me how much, what this value is for a given current, right? Okay, so this is the response here. And what I want to do, figure out how do I relate these sorts of things to what you actually measure experimentally? And what you typically measure is you measure a current response, and you have a voltage signal, and so what you can get is an impedance. So Z, this is defined as the impedance of the circuit, and it's this. For this particular circuit, this one, we're talking about that one, that's the impedance. So the impedance, this is the thing that really I like to think about as the AC equivalent of resistance, because you get basically Ohm's law. Right? So if we know the impedance, we can calculate E and I. But the problem is, in general, the impedance is a function of frequency, because it probably has some capacitances in it, right? And reactance of the capacitor depends on frequency, right? So it's going to be frequency dependent, and it's also going to be a complex number, because there's going to be some phase shift between the applied sinusoidal voltage signal and the current response. So in general, Z omega is going to have a real component and an imaginary component. This is in fact what you measure in the lab experimentally. You measure the real and the imaginary component to the impedance. So the magnitude of Z absolute value, right, the magnitude, and that's just Z squared equals Z real squared plus Z imaginary squared. And then in this RC case, that Z is R squared plus omega squared C squared. So that's just from this expression, right? When you square a complex number, do you remember how you do that? You got to take the complex conjugate. And how do you get the complex conjugate? You change the sign of all the imaginary numbers. So when you do that, the cross terms between the complex and real parts of the number cancel each other, and you just get this expression. Okay. Okay, so that's that. And so what do you measure? Well, again, on the complex plane, we can draw our response, imaginary, and this is going to be the real axis, and we'll have some current, I dot, and we might have some voltage source that gives us that, and E is equal to Z times I dot, right? So we just showed. And we can decompose that into two components. And this component is going to be ER equals R times I dot in this case. And this component on the imaginary plane is going to be EC, and that's just equal to negative JXC I dot in this case. So again, we have our excitation, our current response, some phase between the two, and we can decompose that response into an imaginary component and a real component. And in this case, you can see very clearly how if you had a way to measure the imaginary and real component, then you could extract the resistance and the capacitance from this circuit, right? So if I can measure this real component the real component here, I can get the resistance, because I could just take the ratio of ER over I, and I could measure the imaginary component, and I could get XC, and get the capacitance out if I do the frequency, right? So you see, for this very simple circuit, if you had a way to do this, you'd be set. In fact, exactly what the frequency analyzer and the potentiostat does. So if you think about this, the tangent of theta, tangent is opposite over adjacent, right? So kato. So opposite over adjacent. So in this case, opposite is this, right? So Z imaginary over Z real. So let's think about what the potentiostat's actually doing. Right? We have our voltage perturbation, right, that we're applying. We control that. We have a frequency generator that generates a sine wave in voltage that you're actually putting on your electrode and wiggling the potential, right? And then there's some current that comes off that, right, that might have a different phase and a different amplitude. And the the frequency analyzer can just measure phi directly. So if you know phi, you can get the ratio between these things. And you know the magnitude, right? You know the magnitude, so you can calculate the absolute size of both the real and imaginary components. So measuring the magnitude of Z and the phase shift, the magnitude you get by the ratio of current to voltage, right, at the maximum amplitudes. And the phase shift you get from the phase shift, you can calculate, it's equivalent to measuring the real and imaginary components of the impedance. They're equivalent, right? So I can rewrite this like that, right? And then you can see very clearly how if you knew this, the amplitude of the impedance, which is just the ratio of the amplitudes, and you know this ratio, you can calculate that. And equivalently, you can get, right, the real part. And in fact, it's easier than that. It's actually really easy, right? So if you know the phase shift and the amplitude, what's the real part of this? There it is. Right? So you know the amplitude of the vector, you can calculate the real and imaginary component. And so that's the potentiostat measures, that's what you need. Once you have this, you can interpret it. So then the key is interpreting the real and imaginary impedances. In this case, it's really easy because the real part is only a resistance and the imaginary part is only a capacitor. And so you can extract the capacitance and the resistance really straightforwardly. And then we'll take a break. Just so you know it, we won't use it here. You'll use something called admittance. And this just simplifies the math in certain cases. Like when you're talking about parallel RC circuits, it's easier to use admittance. And we call that Y. It's just defined as 1 over Z. But it's the same. Everything's kind of exactly the same. It's just 1 over Z. It just makes the math a little easier when you're talking about parallel circuits. And sometimes you can measure, you can tell your frequency response analyzers to measure admittance. And then it will give you this value in inverse terms. By the way, the units of impedance are ohms, just like resistance, because it has to convert between current and voltage. These are real numbers now. Well, they're numbers, right? This is the imaginary component of the impedance. This is the real component of the impedance. They're the magnitude of these projections on the x and y, the real and imaginary axes.